All right, so I'm doing a Gauss's law problem. I have a sphere. It's centered at the origin. It has radius a, and it has a volume charge density that is 1 over r squared e to the minus ar. And the first question I'm going to ask myself is, in this problem, what variables matter and what variables don't matter? And the way that I think about this is if I just grab this entire problem and I move it according to one of the coordinate system variables, what happens? If I move it to positive x, that changes things. If I move it to positive z or like positive y, that changes things. So this does depend on x, y, and z. Obviously, we're not going to use Cartesian coordinates here. If I'm smart, I recognize that it's really easy to represent this shape in spherical coordinates. So I start by looking at it in spherical coordinates. And I think, okay, well, what if I change the value? What if I like rotate this in phi? Nothing changes about the problem if I rotate it in phi. Also, nothing happens about this problem if I rotate it in theta. Cool. This problem does not depend on theta or phi. Clearly, it depends on r because I have a volume charge density that does depend on r. So that's pretty straightforward. So cool. The next thing I have to find out for my first couple steps of a Gauss's law problem is if I am looking at my electric flux density at some observation point, I'm going to name it P. What direction is the electric flux density vector? What direction is that? Well, remember when we were doing all of those Coulomb's law and Biot-Savart law things where we choose an observation point and then we choose opposing dq elements at different positions on the sphere, and then we eliminate different vector components? That's exactly what we're going to do here. So if I choose some dq, which remember for a volume charge density, that's rho v times dv. This dq is going to contribute an electric flux density dd. That kind of points that way. But for any dq I choose that does this, I can choose an opposing dq, an oppositely located one, that does this. So any theta-directed components cancel. There is no phi-directed component. And there are components add. So what direction is the electric flux density? It's only in the a hat r direction.
Could you say that one more time, please?
Which part? Where should I start?
The bit about the phi.
Oh
direction
yeah,
and
there's no phi component. So no matter where I choose this observation point, no matter where I choose it, it doesn't, the sphere is symmetric rotationally. So I could rotate the sphere and nothing would happen, or I could rotate this observation point around the sphere along phi and nothing would happen. And also, like,
hockey. Hockey's more important.
I'm sorry, what? I guess you can have a phi component if you choose them opposing this way. I chose them up and down, so there wasn't a phi component. But if I choose them opposing horizontally, I can have a phi component this way, and I can have a phi component this way, and they can cancel. But for any choice I have that creates a phi component or that creates a theta component, I can always choose an opposite dq that will cancel it. Does that make sense?
Yes, and then you said the arc components add.
Yeah, the R components add because they're all
Oh.
always pointing straight out of the sphere.
Okay, so that's how you got.
Yeah.
It only
so
depends on
that's,
A hat R.
yeah, that's how I got that there is only an R component. I want to have you be careful about saying that it only depends on A hat R, because that is close to saying that it only depends on R. For electric field problems, this is often true, but a lot of the time when you're doing a magnetic field problem, you can have something that only depends on R, but also points in the phi direction. So when you're saying something about a vector, it is better to say this vector is R directed, or this vector is phi directed, or this vector is theta directed, rather than saying it only depends on A hat R, or it only depends on A hat phi, because that dependence, the variable dependence, could be different from the vector direction. Right? Like I could have some electric flux density that is a function of theta and phi, but it points in the A hat R direction. And it would be hard to describe that if you're not very careful how you say it.
Okay, so it's